Okay, so we talk about primality testing of a number. We need a prime number. So, for our public key crypto system, so we want to see whether we can get a prime number. Say suppose we need a for RSA, suppose we need 10, we need PQ large prime, say 102 bits. So, we need a number prime which is lies between 0 less than PQ less than 2 to the power this, because this many bits actually. So, huge number. So, now the question is there any algorithm which can give us this many bits prime number. So, is there any algorithm in which we can generate a this is the prime number algorithm, say we will give a input say L is here this, and it will give us a prime which is basically this many bits. So, no, there is no such algorithm exist which can give us a prime number of our desirable size. So, then what is the option? Option is we can just choose an integer, odd integer, and we can test whether this is prime or not. So, we can choose an integer. So, that is those are called primality test basically. We can choose an integer p, and then we check or test. This checking means testing. Check whether this is odd integer, because 2 is usually is taking as a prime, which is a even number, but any other even number cannot be prime because it has a factor 2. So, prime means it has prime number is definition of prime number is it is only divisible by one and p. So, other than 1 and p, it should not have any factor. So, it we should not get any factor other than 1 and p. Okay. So, now we can check whether p is prime or not. So, we have seen this, we can check by suppose for checking this we have to start with, this is a naive approach, we can start with 2, 3, 4 like this, and we can check whether this divides p or not. So, we take a k from this, whether this is whether p has a factor this or not. We take a k from this set, and then we check whether k divides p or not. Okay. Now, this we can reduce by checking up to root over of p, because we have seen if a is a factor which is greater than root over of p, then so a is a factor means there will be a b such that a p is equal to b, then b has to be less than root over of p. So, if we have a factor of p which is greater than root over of p, then we should have a factor, another factor b which is less than 2. So, it is sufficient to check this up to, so 1 we can leave it up to this. Okay. So, but this is not a good idea, because if p is large, so checking too much is, so this approach is not that a good idea. So, this another approach is we have seen, which is called sieve of erythrocenses. So, that idea is we just remove the composite, then just we like this, we just remove the composite, then the remaining number is prime. Sieve of erythrocenes, Okay. So, idea is, so we will just sieve it, I mean we just delete all the composite and then the remainings are the primes. This we have seen, like we first delete, suppose we want to check P is prime or not. I mean we want to consider 1 to n some numbers. We want to get all the primes from 1 to n. So, what we do? We delete all the, we remove all the composite from 1 to n, and then the remaining will be the prime number. So, that is the idea. So, for deleting, what we do? We first delete all the numbers which are multiple of 2. We remove all the number multiple of 2, then we remove all the number which are multiple of. So, multiple of 2 means 4 we delete, 6 we delete, 8 we delete, 10 we delete, like this. Then we delete all the numbers which are basically multiple of 3, but 2, 6 we have deleted, 3, 9, 15, like this. So, then we delete all the numbers multiple of 4, but that will come under multiple of 2. So, then we delete all the number multiple of 5. So, 5, 15 is come under 3 multiple, like this. So, this way, so after this the remaining number will be the prime number. So, this is also not a very efficient approach, because if n is large. So, this way it will take much more time. So, now we want to see whether we can have some better approach to better way to test whether a odd integer is a prime or not. So, for that we need to take help of some properties of prime number, and then we can. So, those are the necessary condition of P to be prime, and then we can use those property to test whether our selected number, our chosen number is satisfying that property. If it is satisfying, if it is not satisfying, then we can straight away say this number is not a prime, it is a composite number. But if it is satisfying, then we can say it could be a prime. So, those are basically probabilistic, I mean those are called pseudo prime, we will come to that. So, let us have this Fermat primality test. Okay. So, this is coming from the Fermat-Little theorem. Let us recall the Fermat-Little theorem. So, what is the Fermat-Little theorem? So, it is telling if P is a prime, let P be a prime number, and A is relatively prime with P. So, GCD of AP is 1. Then A to the power P minus 1 is congruent to 1 mod P, and this is true for all P, all A. This must be true for all A, where GCD of AP must be 1. So, this is the Fermat-Little theorem. So, we want to use this. So, this is a necessary condition to P to be prime. So, if we choose a number P, odd integer, now, and if we take a which is basically GCD, we can calculate the GCD of A and P. Now, if GCD is not 1, then we can say P is not a prime, because they have a common factor greater than 1. Okay. So, then we can say that they are P is not prime, but if the GCD is 1, and if this condition is satisfying, if this condition is not satisfying, then we can say P is not a prime, because this is the necessary condition to be P to be prime. But if this condition is satisfying, then we say P may be a prime. So, that is why it is called pseudo prime, probable prime. So, P is prime base A. So, this base A is coming into the picture, like, because we are not testing for all A. If we can test for all A, then we can sure that P is a prime, but that test is equivalent to that the sieve method we have seen. Okay. So, we will use this. So, let us just write the primality testing of Fermat. So, we choose a P and we check whether P is a prime or not. Okay. So, we select a, choose a such that we choose a randomly and such that GCD of A and P we compute. We choose a such that GCD of, if we choose a and if we found GCD is not 1 greater than 1, then we can straight away say this is not a prime. We chose a less than p, okay, an integer less than p. Then we compute GCD of AP. Now, if GCD is greater than 1, then we can greater than 1, then they have a factor more than 1. So, that means P cannot be a prime, then return P is composite number, not prime means composite. Else, if the GCD is 1, else means the GCD of, else means A is co-prime to P, that means their GCD is 1. Okay. Then what we do? We compute this a to the power, we compute this, we store it into y, a to the power p minus 1 mod p. Okay. So, how we can compute this? This is just a powering a excuse me, powering a number. So, powering. So, this powering we can compute, we have seen for RSA, the so square and multiply method we can use. So, one can do this powering. So, we check this and then we see whether else if y is congruent to 1 mod p, then if y is not congruent to 1 mod p, then return p is composite. For sure. Okay. Else, if it is 1, then it is satisfying the necessary condition, then p is we can return as a prime, but this is also probabilistic sense, because we have only chosen one A. We are not testing all possible A. If we can test for all possible A, and if this for all A's which are having GCD with P is 1, and then if it is giving us that a to the power p minus 1 is 1, then return this composite, else return p is prime. Actually, this is probable prime. That means p is prime base A, we can say, else return p is prime, but this prime is also probable prime. Okay. So, this is the code for Fermat's primality testing. So, this will give us probable prime. We will take some example for this. Suppose we want to test whether say p is equal to 49 is prime or not. Okay. So, p is equal to 49. We want to test by Fermat's primality testing whether this is prime or not. So, how to test this? So, we have to choose a for which the GCD is 1. So, if we choose a is equal to say 19, then we can compute the GCD of A and P, which is basically 1. This for computing this we can use the extended Euclidean algorithm to compute this. So, we compute this. Now, if we compute this, so GCD is 1. So, now if we compute 19 to the power p minus 1, p minus 1 is, so we compute this a to the power p minus 1. So, this is basically 19 to the power 48. So, this will be happen to be congruent to 1 mod p, 1 mod 49. We can verify this. This we can calculate and we can verify this. So, if we just use the Fermat's primality test, it is telling us 49 is a prime, but it should tell us probable prime, because we know 49 is not a prime, because 49 is basically 7 into 7. 49 is not a prime, but it is reporting as 49 is a prime. So, we should use here base 19. So, that means, if we take A is 19, then it is reporting as a prime, which should be a probable prime, but which is not a prime. Okay, so, this is a false alarm kind of thing. Then again, if we choose, so we can try for another A. Okay. So, if we say choose A is equal to say how much? A is equal to say 31. Okay. If we choose A is equal to 31, and then if we compute this, A to the power p minus 1 is basically 31 to the power 48. So, this also you can verify, this is 1 mod congruent to 1 mod 49. So, this is also telling us, for this choice of A, this is also telling us 49 is a prime base 31. Okay. So, now suppose we choose A is equal to say 5. Suppose we choose A is equal to 5. Then we compute A to the power p minus 1, which is basically 5 to the power 48. So, this is not equal to 1 mod p. This you can check. Then this will Fermat's test will report us 49 is not a prime. So, this decision is correct. There is no probability in this decision, but earlier decision probable prime, pseudo prime, prime base this A. So, that is the case. So, if our primality test is reporting that it is composite, so that is certain. Okay, deterministic way we can tell this is composite number, but if our probabilistic algorithm test is telling this is prime, then it could be it should be a probable prime basically. Okay. So, this is the Fermat's test, primality test. Now, we talk about Miller-Rabin primality test, that is also probabilistic test. So, this is Miller-Rabin. So, we have a p and we have a odd integer p, and we want to check whether p is prime or not. So, idea of this test is, if so p is odd integer. So, if p is prime, so let p be a prime, then what we have, then p minus 1 must be odd, and that should be written as 2 to the power k into m, where 2 and m are relatively prime. Otherwise, if they have a factor 2 again, we can take that 2 here. So, there should be some k such that this k could be 1 also, okay. But at least there should be 1 k, because this is odd, this is even number, because p is odd number. Okay. So, this is the case. Now, by Fermat theorem, we know A to the power p minus 1 is congruent to 1 mod p. So, that means A to the power p minus 1 by 2, this has a square root plus minus 1. So, now what is A to the power p minus 1 by 2? A to the power p minus 1 by 2 is basically A to the power 2 to the power k minus 1 into m is congruent to plus minus 1 mod p. So, either it is plus 1 or it is minus 1. So, either this is yeah. So this can be written as a to the power m to the power k minus 1 is congruent to either it is plus 1 or minus 1. So, this is the properties of prime. So, this is the necessary condition. So, if p happen to be a prime, it should satisfy this. So, if it is not satisfying this, then we can say p is not a prime number. So, that is the test basically. So, we check whether a to the power m is congruent to 1 mod p or not. If it is not, then we check. So, if we take this as b a to the power m, then we check whether it is actually plus minus 1. Then we check square of it. We check the b square is congruent to minus 1 or mod p or not, like this. So, this condition must satisfy. So, that will give us the a test, necessary test. So, let us write the test, Miller-Rabin primality test. So, this is the code for, let me just Miller-Rabin. Okay. So, p we write it as this, p 2 to the power k into m, where 2 and m are GCD is 1. So, we compute b is a to the power m. So, again we have to choose a such that GCD of a and p is 1. So, this has to be there. So, we choose a. If we randomly choose a and it happened that GCD is not 1 greater than 1, then we report p is not prime. So, that part I am not writing. Choose a such that the GCD is 1. Then we compute this b a to the power m mod p, where m is this. Okay. Now, if b is 1 mod p, then we return p could be a prime, then return p as prime. It should be probably prime or prime base a, something like that we have seen. Else for, because now we have to check whether b square, b q, they are giving us this minus 1 or not. If they are giving us minus 1, then this condition is satisfying. Sorry. So, for I is equal to 1 to k minus 1, we keep on compute b. So, under this loop, if b is congruent to minus 1 mod p, this first step is checking whether this is plus minus 1 or not. Then also we return p is composite, sorry, p is prime, it should be probable prime. Else, so under this for loop, else we compute this b square, b is replaced by b square mod p, and then we run this loop, and once we complete this loop, so 6, 7, 8, once it complete this loop, then we return n is composite, p is composite. P is composite. Okay. Then we return p is composite, because we have tried for all possible, because this is up to k minus 1. So, this is, so let us take an example, quick example for testing this. If it is returning composite, then it is surely a composite number, there is no probabilistic sense, but if it is returning a prime, then this is a probable prime or pseudo prime base A, we can say. But anyway, this is the test. So, let us take some example. Okay, suppose we choose n is equal to 105. So, we know 105 can be written as this factor, but we are pretending that we do not know this, we are unable to factorize this, that we are pretending. Okay. So, now we want to write this is p, now we want to write p to be 2 to the power k into m, where m and 2 is relatively prime. So, 105 is basically, so p minus 1. So, p minus 1 is basically 104. So, this should be written as 2 cube into 13. So, here k is 3, m is 13. Now, we choose a, say a is 8, such that there is GCD of a and p is 1, and then we compute a to the power 13, this a to the power n mod 105. So, this is give us 64, and then we compute again 64 square mod. So, this is b. So, b square again mod 105, this is giving us 1. So, that means 64 is a square root of 1, is a square root of 1, and hence 105 cannot be a prime, 105 cannot be a prime. So, it is a composite number. Okay. Since it has a 64 is a square root of 1, hence 105 cannot be a prime. Okay. So, let us take another example, say this example we have seen n is equal to say 49. Just now we use this example for Fermat. So, let us apply here also. Suppose we take p is equal to 49. So, what is p minus 1? P minus 1 is 48, which is basically 2 to the power 4 into 3. So, m is 3 and k is 4. So, what we do? So, if we choose the if we choose a to b, but we have seen if we choose a is 18, then 18 to the power m mod 49 is 1. So, which is giving us this 49 is a prime, but base 18. Okay. Similarly, if we choose a is equal to 19, so 19 to the power 3 mod 49. So, this is also, so this is basically congruent to, this is basically 1. So, this is also basically minus 1. So, this also is giving 49 is a prime base 19 like this. Okay. Now, if we choose a is equal to 5 say, then what happened? Then we compute a to the power m mod 49. So, this is our b. So, this is basically 27. Then we compute 27 square mod 49, this is basically 36. Then again we compute 36 square mod that for loop, this is basically 22. Now, we stop because k is equal to 4, 3 times we have to do, which is not minus 1. So, this implies 49 is not a prime, is not a prime. So, that is guaranteed. Okay. That is for sure 49 is not a prime. Otherwise, if it is reporting a prime, so this should be probable prime. Otherwise, we have to check for all possible a. Okay. Thank you.